So now let's talk about the ratio and root test. So as you can see, the ratio test has the following. If the sum of a of n is a series of non-zero terms, the sum will converge absolutely if the limit as n goes to infinity of the absolute value of a of n plus 1 over a of n is less than 1. And if that diverges, if that's going to be greater than 1, and if it's equal to 1, then the ratio test is inconclusive, right? So we get to use another test. So for example, if I'm going to use the ratio test on a, okay, what I would do is I would take the limit as n goes to infinity of the absolute value. Now, notice that I have a of n plus 1. So I'm going to rewrite this as 2n plus 1 over n plus 1 factorial. Now, if we divide this by the original equation, right? If we divide this, and I, again, don't write this down because I'm about to rewrite it again anyway. If I divide this, I would actually keep change and flip. So this part right here would be the same thing as multiplying by n factorial over 2 to the n power. Right, now there's going to be a little bit of simplifying that you probably have to do on here. Now, I'm going to rewrite a couple of things just to make it easier for you to see what I'm doing. So 2 to the power of n plus 1 could be rewritten as 2 to the n power times 2 to the first power. Remember, when you multiply two exponentials, assuming you have the same base, then you add the powers, right? Now this right here, n plus 1 factorial, I can write this as n plus 1 times n factorial, right? Because remember, a factorial, for example, it'd be like 5 factorial would be the same thing as 5 times 4 times 3 times 2 times 1, right? So I could write 5 factorial as 5 times 4 factorial. So that's basically what I'm getting that from. Times n factorial over 2 to the n. Now, notice that this is going to cancel with this. N factorials are going to cancel. All right, and if you think about it, what I have left here, right, even though it's the absolute value, 2 to the first power is not ever going to be negative. So I can, and n plus 1, since n is our positive value starting with 1, then basically this right here, I can just get rid of the absolute value signs because this will never be negative anyway. All right, now I can take the limit. The limit, as you can tell, is 0. And because 0 is less than 1, then the series is going to converge by the ratio test. Well, let's look at B, right? Same idea. We're going to do the same thing. So now we have the limit as n goes to infinity of the absolute value of this right here, but I'm going to add a 1. All right, so I have a n plus 1 plus 1, which would be an n plus 2 factorial here, over 3n plus 1 times, I don't know what it is, but my dogs always decide to drink water right when I'm recording. All right, so now I have n plus 1 here, factorial. Remember, I keep change and flip, right? And this is 3 to the n. Okay. Now, if I simplify this a little bit, some of you guys are going to be able to you don't really have to write this if you can see it, but if you can't see it, then write it out. Okay, so n plus 2 factorial, I can rewrite that as n plus 2 times n plus 1 times n, or I can write this as n plus 1 factorial like that. 3 to the n plus 1 can be rewritten as 3 to the n times 3 to the first times 3 to the n over n plus 1 factorial. Okay, so let's cancel some stuff out now. The 3 n's are going to cancel. N plus 1 factorials are going to cancel. And notice that what I end up with is going to be n plus 2, which will be positive because the n is positive, over 3, which is also positive. So I can just go ahead and drop the absolute values at that point. notice that this right here is going to be infinity. Okay. So if this is infinity, because this is going to be greater than 1, right? It doesn't really matter. Well, I guess it does matter it's infinity, but because it's greater than 1, according to the second scenario here, then this will diverge by the ratio test. Okay. Because that's greater than 1. Okay, so let's go on to number 3, or example 2, excuse me. And again, we're using the same ratio test, so same idea. We're going to take the limit as n goes to infinity of n plus 1 over 3, or cube root of n plus 1, divided by n over cube root of n, which if I flip that, right, because I'm dividing, I would have this. Now, there's not a whole lot you can actually, there's pretty much nothing you can cancel on this. Okay, so what I'm going to do instead is I'm going to rewrite this as I'm going to put basically this and this together. 7n plus 1 over n times, and I'm going to put now this and that together. Okay. And when I do that, I can actually rewrite that as the cube root of all of this, n over n plus 1. Now, none of these are going to be negative anyways, but so you can drop the absolute value or keep it in if you want. It doesn't matter. But essentially, I can take the limit of this and then multiply it times the limit of this other side right here. Okay, the limit of this one right here, it's 1, right, using the horizontal asymptote rules. Now, in this one, you can look at the inside and then find out the limit of that, okay, and then take the cube root. So in that one, it's 1. The cube root of 1 is also 1. Again, I used the horizontal asymptote rule for the inside of that. So 1 times 1, it's 1. Now, 1, according to this, that means that the ratio test, there's no conclusion with the ratio test. And what that would mean to you is that you would have to use a different method. Okay, so I can say use another type of test. So it doesn't really say that it can't be done. It just says that this one doesn't really tell you. You have to be able to use another test. All right, so let's go on to the root test. Okay, so the root test for convergence or divergence works well for the series that involve nth powers. It's important to note that the root test is always inconclusive for any p series. Okay, so that's kind of important to note there, but let's go on. So on example 3, all right, notice that you have sort of this weird formula. Notice that you have the sum right here. And if you take the nth root of the absolute value, and if you have the scenarios, then it'll tell you what it is. Okay, so whether it's converging or not, or inconclusive. Okay, so, excuse me. So for this one, by the way, this is a of n according to the formula. So I'm going to rewrite this as the limit as n goes to infinity of the nth root of the absolute value of e to the n over n to the n. You could also, because I know that this are going to be positive right here, I shouldn't say also, but in addition to that, I'm just going to simplify this. So because what I just said, right, that's all, the inside of this would be positive, I can just drop the square, I can drop the absolute value. And then I would have e over n to the nth root, right? So essentially what I'm trying to tell you is that would leave you with the limit as n goes to infinity of e to the n. And in this case, this would be 0. Now, because 0 is less than 1, then this is going to absolutely converge. Let's see how they wrote it on the homework. Want to use the same terminology, but can't find my homework. So absolutely converge. Okay. So moving on this one right here. Okay, same idea. If we take the absolute value of this is going to be positive anyway. Okay, so I'm not really going to write the absolute value when I write the limit, because I know I'm going to have to get rid of that anyway. But what I can do is I can take the nth root. Now remember, the nth root is the same thing as erasing this to the power of 1 over n. Okay, so that's sort of good to note, because that sort of helps you sometimes see this a little bit better, right? So I can simplify this as the limit as n goes to infinity of n to the power of 3 over n over, well, this times this, right? If I multiply that power and that power, that's basically going to give me 1. So 3 to the first power. So that's all I can do in terms of simplifying. Now I have to figure out what the limit is, right? First step is I can take the 1/3 out. And now my job is to find out what this would be equal to. Now, on this one, you got to think about it a little bit. If I take this limit to infinity, right, that up here, the power will approach 0. So therefore, I would have n to the 0 power, which would be 1. So essentially, this is the same thing as 1/3. The limit as n goes to infinity of n to the power of 3 over n would be 1. So the answer is 1/3. And because that's less than 1, according to the root test, then you're going to have, this will absolutely converge. Okay. All right. So let's go ahead and move on. This one, I think, is probably one of the easiest ones, because by the time, again, if I take the absolute value of this is still going to be positive no matter how I do this, all right? It's always going to be positive. So therefore, I'm not going to write the absolute value when I write the limit. Although I do want you to understand that it is there. Where it helps is if you have some kind of alternating sequence. All right, so now I have n over 1 plus n cubed. Now you can write this as to the power, raise this to the power of 1 over n, or you can take the nth root of this. Sorry, I forgot this. So when I take the nth root, basically it eliminates the power. So I have n over 1 plus n cubed. If we take the limit as n goes to infinity, right, but the horizontal, kind of using it the same way as the horizontal asymptote rules, this would be 0, all right? And according to this, if it's less than 1, then it absolutely converges. So, or converges absolutely. Okay. So that's that for that. Let's go on to what I think is actually very useful in this homework, because by now we have 10 tests for determining convergence or divergence, right, or of an infinite series. And at times more than one can be applied. So the 4 questions to consider, all right, before you start deciding what type of test to use is a geometric or a P-series, alternating or telescoping. Now, I'm always looking for these. And to be honest, right after that, then I start looking, after that, I almost do this immediately. I kind of do the nth test almost right away, because the nth test is really easy. I can almost do it in my head, right? Now, the nth test is the one that says if you take the limit as n goes to infinity and you get, let me not mess it up, if you get something other than 0, so if the limit, let me write it right here. If the limit as n goes to infinity of a of n is not 0, then the series will diverge. Now, if it's not 0, then it's inconclusive. It doesn't. You can't really say that it diverges or converges, right? But those are the easiest ones to tell. Now, on A, for example, all right, anytime I have a constant raised to a power, I automatically think of a geometric series. Okay. Now, on a geometric series, and I can't think of the formula for it, but it's something like this, I think. Something like that, okay? I think this one's A, though. R of n, R is the kind of like that ratio, and R in this case is this. Okay, so I know that my R, or the absolute value of R, which in my case is pi over 3, since that is greater than 1, right? Because pi is 3.14. So that's going to be greater than 1. If it's greater than 1, then the series will diverge. If that's less than 1, like 1/3, 1/2, I don't know, something like that, then it will converge, right? So I'm done with that one. So that's all I need to do on that. Now, for example, on B, I automatically think nth term test. Now, the nth term test says that if you take this to infinity, if you get 0, then it's inconclusive. And unfortunately, this one will be 0, so it's inconclusive. I can't really use that test for it. That I think, is this a P series? It's not. But when I see something like this, I think of comparing it to something simpler. Right. So what I do here, first of all, I don't really know. The most confusing tests for me are the comparison tests that came from the section 9.4, I believe. So let me look at them real fast as I say this, because I don't want to mess them up. All right, the comparison test. Those are the most confusing for me to use, but let's just do it like this, okay? First, I'm gonna compare it. Let me write this over here. I'm going to compare this to 1 over n, right? Kind of the parent, kind of like I told Brock one time. Just think of the parent function of this, of the bottom part. Okay, so that would be 1 over n. Now, I know that 1 over n is divergent. Now, here's the part that I normally don't. I remember that pretty well. The one I don't remember pretty well is the following. In order for me to figure out which test to use, I have to figure out which one's bigger. Okay. Now, this one's going to be bigger. Okay. Now, you can plug in numbers and check me on that, but that one's going to be bigger now because that's going to be bigger. And according to 9.4, it says that if you want to know, if you think something is converging, the series you compare it to should be larger. Okay. So, and if you think the series is divergent, then the thing you're comparing to should be smaller. So this doesn't work. All right. It doesn't work for the direct comparison. So what it works for is for the limit comparison test. Okay, so what I compare it to is divergent. That's a harmonic series or a P series, whatever you want to call it. This is what that is. That's divergent. Okay, so what I'm going to do with that, just to kind of a quick reminder, what I do is I do the limit as n goes to infinity, not 1, infinity, of 1 over 4n plus 1. And then I'm going to divide that by the thing I'm comparing it to, all right, which in this case is 1 over n. Now, if I keep change and flip, that would be the same thing as multiplying this by n times n over 1, excuse me. Right now, this is going to give me the limit as n goes to infinity of n over 4n plus 1. So the limit of this one is 1/4. Now, because this right here, the limit is between 0 and infinity, according to the limit comparison test, okay, then this will be divergent. Basically, this will also diverge because this is divergent, okay? If this would have been convergent and I would have got something that fits this, it has to be between 0 and infinity, then this would have been convergent, all right? But since the thing I compared to is divergent, this is also going to be divergent. All right, so let's go to C. Now, on C, this one's easy. Again, remember, I always think, is this a geometric P series? And right after that, I just test it real quick in my mind. Is this, if I take the limit as n goes to infinity, is that going to give me 0? If it's 0, I'm screwed, all right? I cannot use the n test. But in this case, it's not 0. So again, this one will be the nth term test. Where I take the limit as n goes to infinity of n plus 1 over 4n plus 1. And that is going to give me 1/4, right? It's the same thing as the horizontal asymptote rules, excuse me. Now, because this is not 0, okay, that's the important part, then this means that the series will diverge. If it's 0, then I don't know if it diverges or converges. So that's why I can't use the nth term test every time, because it doesn't tell me everything. It just tells me if something is diverging. It does not tell me if something is converging. Okay, let's look at D. On D, I'm not really sure. Again, I think of the nth term test first, because that would be the easiest thing for me to do. This will grow faster than this, so this will be 0, so I can't really use that. So I have to think of something else. This is not a p-series. This is not a geometric, all right? So at this point, I have to think of something else. Now, I've noticed that at that point, then I started thinking of integral. Could I integrate this? That's really the question, assuming you have the skills to do it, right? Could I integrate that? And the answer is yes, I can. Okay, so I'm going to at least attempt the integral test on this one. And the integral test says that if you take the limit as, let's call it a goes to infinity, I'm going to do an improper integral. Let's see, between 1 and a of this right here. Let me switch this to x's real fast. Now for this one, I'm going to use u substitution, where u is x squared and du is 2x, but I do not need that 2. So I replace this, right? I would have the limit. I would have the limit as a goes to infinity of 1 to a of 1/2 here. Let me think about this for a second. It will be 1 over u, 1 over e to the u, or I can write this as e to the negative u du. If I integrate this, that would give me a negative. That would be some kind of other substitution there, but hopefully you can see that this will just be negative e to the negative u. I'm going to go ahead and replace that u, however, with the u that I have here, which is x squared. Okay, so this will be the same thing as the limit as a goes to infinity of negative e to the negative a minus a negative, which would make it a plus, to the negative 1, like that. Now, e to the negative a, or negative e to the negative a, now remember, because that's a negative exponent, this would actually go to 0. Basically, that would be the same thing as 1 over e to the a, so that would, if I make this really big, that would the limit would be 0, okay? So that's 0. So that's going to leave us, and I forgot the 1/2 all throughout. Just realized that. So I was missing a 1/2 here, a 1/2 here. So the answer to this would be 1 over 2 to the e. Now, on the integral test, unlike the nth term test, what that says, if you get something other than 0, then if you get any kind of number here like you were doing there, then the series will converge. Okay. All right, moving on. Integral test, not a whole lot of fun because you actually have to do a lot of work sometimes. Now on E, I can use the alternating series test. How do I know that? Because, well, this is an alternating series, right? Okay, and if you remember the alternating series test, I'm only gonna take the part that's not alternating, if you will. All right, so first step is I have to find out if this right here, just the sequence, not the not the sum, just the sequence. I have to figure out if that's gonna be positive, and it is. And so check on that. Number two, I have to make sure that it's decreasing, and it is, right? Hopefully you can see that. The sequence is decreasing. And then on number three, then I have to see if the limit as n goes to infinity of 2 over 3n plus 1, if that's equal to 0, and it is, then this means that the series will converge. All right, let's see. What's F? F is that. Okay, so that one should be a little bit more familiar because I literally just covered it. On that one, I'm going to use the root test. How do I know that? Well, because it's being raised to the nth power, and I know if I use that root test, that gets rid of the n, okay? So according to the root test, I would have to have the absolute value of this, but all of this will always be positive. So that's why I'm not gonna put the absolute value on there, but it is part of the formula, okay? So that says that what I can do is I can take the limit as n goes to infinity of the absolute value of the sequence. Now again, I'm not gonna put the absolute value. And then all of that, I have to take the nth root. Now the nth root, you can write it as raising all of this to the 1 over n, or you can do it like that. It doesn't matter. My point is that by the time you take the nth root of this, you end up with n plus 1 over 3n plus 1, and the limit as n goes to infinity should be 1/3. All right, now on this one, I do have to go back and look, okay? According to this, let's see, that's the ratio test too far. Because that's less than 1, right? I'm looking here. Because that's less than 1, then the series will converge. Okay. By the root test. All right, and then finally we got G. Now, I don't know if this happens like this all the time, but when I see a factorial, then I automatically, and because I already did the homework, right? Then I automatically start thinking about the ratio test now. So let's do the ratio test, which is what we did at the beginning here. Okay, so the ratio test says that if you take the limit as n goes to infinity of, I'm going to write exactly the same function, but I'm going to add a 1 to it. So n plus 1 factorial instead of n factorial over 3 to the n. Whoops. Then I'm going to divide that by n factorial over 3n. But when I divide, I will keep change and flip. Oh, by the way, I forgot to put a plus 1 here. I will keep change and flip, and I'm going to end up with this, right? A little bit of simplification like I did at the beginning. Remember, n plus 1 factorial, I can write that as n plus 1 times n factorial all over 3 to the n times 3 to the first, which would be 3 to the power of n plus 1. 3 to the n over n factorial. Let's see, n factorials cancel, 3 of the n's cancel. So now, again, what I have remaining will always be positive, so I'm going to get rid of the absolute value. So I have n plus 1 over 3. So this is going to be infinity. Right, and because of that, because that's going to be greater, let me look before I lie to your face. Because infinity is going to be greater than 1, and that's going to diverge. Now, the next page on there just sort of has a summary of tests and sequences and series. Some of it I find helpful, some of it not so much because they have so much algebraic calculus jargon that it's kind of hard to follow sometimes. Let me see if there's something on the homework real fast that kind of gave me some trouble that perhaps I need to address. Let's see, before I let you guys go. Oh yeah, let's quickly look at number 18 here. I already have it open. Stop it. All right. So on number 18, all right, as on this one, you're supposed to basically use your best judgment and use whatever test you like, okay? Now, of course, like I told you, I always look for the p-term test and look for the geometric series. This is neither one. So what I did after that is that I did notice relatively quickly that I can compare this if I wanted to. I wish this would have been like pi n, and you know that's an alternating series, but I noticed that this, you can compare it as 1 over 2 to the n. Now, when I looked at the answer, I was a little bit confused because they had, let me look what they had here. Where are you? Homework. Yeah. And remember, you can look at it as a p-series or a geometric series. It doesn't matter. We can call this, actually, I don't know what that would be, a p-series. I consider this a geometric series because you can rewrite it like this. All right, so on the geometric series, because that ratio is less than 1, this will converge. Okay, so I was like, okay, but I didn't think I could use that because this right here is positive, and I looked on my calculator, it's positive until you get to n is equal to 8, then it goes to negative. Okay, so I guess in essence, this is sort of a alternating sequence. Okay, it's just not what I'm used to. So because of that, then I had to go look at 9.4 or 9.5, excuse me, when they talked about absolute convergence. All right, and the absolute convergence says that the absolute value of this sum if you can prove that this is convergent, then this is also convergent. All right, this is like the last part of notes 9.4. Okay, so that's basically what I said to do after that, though. So I compared it to that, right? I knew that was convergent. So with a comparison test, and this is a direct comparison test because this right here, and that's the other part that I was like, this is really weird. The absolute value of this, let's see, will be bigger than 1 over 2n. Now, hold on, let me see if that's true, because that's the direct comparison test I just noticed. Or at least I'm proving it with that. Hang on just a second. Direct. It's the other way around. And the direct comparison test, as you can tell, that's the one that gives me the most trouble because I cannot remember what sign. So this is bigger, and because this is convergent, then this will also be convergent. This is what they call absolutely convergent. So that was the most tricky one of them all in the homework. Okay. So, anyways, guys, that's pretty much it. I hope I didn't talk too much, but feel free to talk trash about me. I really can't hear you. It's just a video anyway. All right, guys. Until next time.